IROC of sinusoidal functions, and IROC is basically instantaneous rate of change. The key topics for this video are the changes in IROC of sinusoidal functions, and then the local extremas of different domains of sinusoidal functions. So for our first task, we need to describe how the instantaneous rate of change varies along a sinusoidal curve. For this, we're going to use sin x as our reference. So before we get into comparing the original function and its derivative, we need to know that when f of x is increasing, f prime of x is greater than 0, and when f of x is decreasing, f prime of x is less than 0. So here we have our sin x graph, and we see that the derivative of sin x is cos x. But how do we know this? So over here, we can determine the slope at pi over 2 is equal to 0. And also over here, these are pretty easy to determine that they're equal to 0. But how do you determine that this is 1 and this is negative 1? Let me prove that to you. So we can estimate the IROC at x is equal to 0 using a secant line. And we're given this interval. So to find the rate of change over this interval, this is how we need to set up the equation, and we reduce sine of 0 pi over 1000 to 0 because anything divided by 0 basically 0. And then when you plug all this into your calculator, you get this answer, which can be rounded to 1. So that is how we know that the slope at this point is 1. And then this is decreasing, so the slope at this point would be negative 1 because they're symmetric. And then also just the fact that this is the original function, it's increasing, and you can see that when it's increasing, f prime of x is positive, and it's decreasing over here, and then you can tell that f prime of x is negative. So the conclusions that we can make from that is that the IROC of a sinusoidal function is periodic, and it ranges from max value of 1 and a min value of negative 1. We can also see that the IROC of a sinusoidal function is also another sinusoidal function, because sin x was a sinusoidal function, and so was cos x. Our second task, we need to consider the same function, sin of x, but we're given a domain which is from 0 to 2 pi. X is equal to our real numbers, and we need to find how many local maximum and how many local minimums are there. So this is the same graph. This is our domain from 0 to 2 pi, and we see that over here we have a local max at x is equal to 2, and we have a local min at x is equal to 3 pi over 2, but there's just one local max and one local min. So there's only one of each over this interval. For our last task, we need to refer to the question that we just did, and we need to see how the number of local extremas change if the domain is basically not limited. It's just all real numbers. So the same graph, but instead x can go up to 6 pi, 8 pi, 10 pi, 12 pi, whatever, how many pi, and also the same thing into the negative direction, so it can be an infinite amount of pi. And I just wanted to pull up the unit circle to give us a visualization of this. So we start at 0, let's say, and we go one turn, and so that's one period. That's 0 to 2 pi, and we know that we had one max in between that period and one minimum. So we go again. That's 4 pi. So then we're going to have 2 maxes, and we're going to have 2 mins. And then we go again, and we're going to have 3 maxes, and we're going to have 3 mins. So the more we go, whatever direction, we're going to have an infinite amount of local extremas, both local maxes and local mins. So before we end off, just fill up this exit ticket. It's just a simple question. Find the derivative of y is equal to 4 sine x. Just pause and try this out, and then I'm going to move on to the answer. So this is our answer. We just basically isolate sine and we take the derivative of sine, which we know is cosine because we just proved it, and it's going to be 4 times cos x. And that is our answer. Thank you for watching.